All right, next one up. So let's take a look at PostLab 5, determination of an equilibrium constant and temperature dependence. So we're going to look at temperature dependence of we're going to take a look at temperature dependence. All right, so my experimental value, my K average was 400. We're going to need that information, I believe, for this. So my K average was 400. Um, sure, good enough. All right, so question one. A solution is prepared by mixing 35 mils of an iron solution and 15 mils of a KSCN solution. Using your average K value, predict the concentration of FeSCN2 plus, an ice table setup and solution required and all of that. Okay, so using our ice, so we're given K. I'm asking for equilibrium numbers. Again, there's only two ways this happens. Either I provide you an equilibrium value or equilibrium values, and you provide me K, or I provide you K, and vice versa. We know that this is going to be an ice table, so we need two things. We always need two things. One, my equilibrium. We always need the equilibrium. That's first and foremost. And I know this is going to be tight, so I'm going to try to SCN minus is in equilibrium with FeSCN2 plus. I'm going to set up a little table here. There we go. Initial change equilibrium. I like to separate out my equilibrium. There we go. This is all molarity, so I'm going to put that in parentheses there. What do I know before I even look at the data that I have? Oh, yeah. The other thing that I need before I even fill in any of these numbers, I also have to write out the K expression. K is concentration of products, which is my SCN 2 plus complex, all over the iron times the concentration of SCN minus products over reactants every single time, products over reactants. So now we're going to plug in the information that we have. I don't actually have, I do have to determine the concentrations of these things. And so I'm going to make this a little bit quicker. I have volume, I have concentration. So, but again, I combine these together to get a total volume of, was it 50 mils? So this concentration is a little more dilute. Because we are doing a dilution, we have to essentially do a dilution. So what is the actual concentration of my iron initially? Well, this is the concentration, but because we dilute to 50 mils, we have to do some math. So I'm just going to do the iron up here, and I'm going to let you set you loose on the thiocyanate. But I think this is all the information. We are doing a dilution. V1C1 equals V2C2 or V1M1, whatever you want to say. My initial volume is I have 35 mils at a concentration of 0.00120 molar. My new volume is 50 mils. I want to know what my new concentration is going to be. So if I solve for concentration, mils is going to cancel, leaving behind molarity. I end up with a value of, for iron, 8.4 times 10 to the negative 4. There's my concentration of iron. Again, V1C1 equals V2C2. We're going to do the same thing for thiocyanate, but I can tell you what it is and you can check your answer. So my initial concentration for iron is 8.4 times 10 to the minus 4. My thiocyanate is 5.4 times 10 to the minus 4. So that's what you should have there. Do I know any other numbers? I do know that I have 0 iron thiocyanate to start. I do know that I have 400 as my value of K. Okay. That's pretty much it. Um, I know that I am going to be losing reactant and I'm going to be gaining product. So in the end, I should be able to do my equilibrium. My equilibrium is going to be 8.4 times 10 to the minus 4 minus x and 5.4 times 10 to the minus 4 minus x. And I should end up with just x for the uh, iron thiocyanate. These are my equilibrium values. Well, now that I have equilibrium values and I have a K, I can plug them in to my K value. So X, my iron was 8.4 times 10 to the minus 4 minus X, 5.4 times 10 to the minus 4 minus X. And we hate this because this is going to be a quadratic equation. Again, make sure that you're using your own K, whatever you guys had in lab. So here we go. So first thing I'm going to do is I'm going to leave this side alone. And I'm going to just distribute. I end up with 4.54 times 10 to the minus 7. That's 8.4. Again, distribute this, those two, and then finally the x's. Hopefully you know how to do that. Better know how to do that. Minus 8.4 times 10 to the minus 4 minus 5.4 times 10 to the minus 4 and plus x squared. Now I can cross multiply. So 400 times this whole mess, which is the quadratic, well, the beginnings of the quadratic. I'm going to cheat a little bit. There we go. All equal to x. So when I finally distribute that 400 through, I'm also going to combine terms as well. So what we end up with, actually, I'll combine after this. So I'm going to distribute this through. I end up with 1.82 times 10 to the minus 4 minus 0.336x minus 0.216x plus 400, 400x squared equals x. I'm going to combine terms, 1.82 times 10 to the minus 4 minus 0.552x plus 400x squared. We have to get it equal to 0, so I need to subtract x from both sides, right? In order, and actually I'll do it from this one. Subtract x from both sides, and we end up with, and now I'm going to rearrange. I'm going to put my x squared first, 400x squared minus 1.1 or 1.552x plus 1.82 times 10 to the minus 4 equals 0. So my values. In the end, there's my A, there's my B, and there's my C. So A, B, C. Oof. Okay, so now that we have that, we have to plug this into the quadratic. The quadratic is a nightmare. It always is. Even I dislike it. No one likes the quadratic. So with those values for A, B, and C, here we go. I'm going to run into the other thing, but that's fine. So x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. And so now I just begin. X is equal to 1.552 because it's been negated, right? Negative, negative. That turns positive. Fine. 1.552 plus or minus square root of negative 1.552 squared minus 4 times 400 times 1.82 times 10 to the minus 4 all over 2 times 400. So I'm going to do this math now, and I end up with two x values. X is equal to 3.76 times 10 to the minus 3. This is when I am adding. And when I am subtracting, my x is equal to 1.21 times 10 to the minus 4. So those are my two values of x. one of those has to be correct. They can't both be correct. Normally, we would get rid of a negative because negatives don't make sense because it's impossible to have a negative concentration. But if we look at these two values, and I'm actually going to just copy these for above, copy, paste, beauty of having an iPad. So if I look at these values as compared, if I subtract this minus this here, we are going to end up with a negative concentration. So we cannot use this as a value. It is too high. We end up with a negative concentration of iron and thiocyanate. So my X value has to be 1.21 times 10 to the negative 4. What that ultimately means is the concentration of SCN2 plus at equilibrium is equal to 1.21 times 10 to the negative 4 molar. There we go. There is the concentration at equilibrium. Oof, long way around. Luckily, most of the time we actually can just skip using the quadratic in the future, but that's what we end up with here. And in fact, most of the time we are not going to need it. So moving on to the last question here. Calculate the absorbance expected for this solution. Again, we're going to use the experimentally calibrated one. So you're going to have to use from lab 1 your calculation 2084.1 concentration of FeSCN 2 plus. I believe this is one I used in the last video anyway, plus 0.0127. I'm going to plug in my concentration of FeSCN 1.21 times 10 to the minus 4 molar. Solve for absorbance. I'll let you do the math. 0.265 is my absorbance. There we go. Good to go. There it is. So that is much quicker than the previous one. And that's done. So again, you're going to find all of this in the link below on Google Drive, should you want this, the actual post lab. All of them are going to be posted there. So, all right, good luck. Let me know if you have any questions.